Hello students. In today's video session, we are going to study another very prominent dimensionality reduction technique which is called as singular value decomposition. So we have seen principal component analysis, which is one of the dimensionality reduction techniques. Also, we have seen ICA, independent component analysis. The next one that we have is called as singular value decomposition technique. Now here also we are interested in obtaining only those features or characteristics which provide the maximum information, and the other features can be ignored. So in this session I'll take an example as to how a singular value decomposition matrix can be obtained. So we have been given a 2 cross 2 matrix A, which is equal to 2, 2, minus 1 and 1, and for this particular matrix we are supposed to find the singular value decomposition. Now this matrix A can be split into three major elements or components: U, summation and V transpose, where U and V transpose are nothing but unitary matrices which are orthogonal, and summation is a rectangular diagonal matrix of singular value. You will understand these terminologies as and when we solve the problem sum. So basically what we do is the matrix is split into three elements: U, summation and V transpose, and when we apply some formulas on these three elements and multiply, we must get back our original matrix A. So this is how singular value decomposition works. So the formula to calculate U, which is one of the unitary matrix, is nothing but U1, U2. Now U1, U2 basically depends upon how much is the dimension of the matrix. So because it is 2 cross 2 matrix, we consider U1, U2. If it would have been 3 cross 3, then it would be U1, U2, U3, which is nothing but 1 upon singular value of 1, which is denoted by sigma 1 A into V1, comma 1 upon sigma 2, that is singular value of 2 A into V2. We will see how these values are calculated. The diagonal matrix of singular value. Okay, so whatever singular value you get, you multiply it with an identity matrix, and that will be giving to you the rectangular diagonal matrix. And V is another unitary matrix which is orthogonal, where we have to find out eigenvectors denoted by this particular symbol, nothing but V1 and V2. So understanding singular value decomposition basically needs a prerequisite on how to calculate eigenvalues and eigenvectors. If you all have not seen those videos, ensure that you check out the videos of how to calculate eigenvalues and eigenvectors under principal component analysis, which I have already taken in my previous video sessions. Now what is the first step? We have been given matrix A. We have to simply determine its transpose and multiply it with A. So first step is A transpose A. So the matrix A has been taken with its respective transpose and multiplied with A. On carrying out matrix multiplication, you get the final matrix as 5, 3, 3 and 5. Alright. Now the next step is to find out the eigenvalues. Now this matrix that we have got, A transpose A, is nothing but your S. So I've denoted it by S. So it is S minus lambda into I is equal to your 0, where we need to find out the determinant of this particular equation. So S is nothing but A transpose A value that you get minus lambda. Because it is a 2 cross 2 matrix, our identity matrix will also be a 2 cross 2 matrix 1 0 0 1. Lambda is multiplied inside the identity matrix and both the matrices are subtracted. Then we find out the determinant of this particular matrix and equate it to 0. On multiplying and carrying out the determinant, we get a equation. Lambda square minus 10 lambda plus 16 is equal to 0. When we solve this manually or by putting this in the calculator, we get two values of lambda. Lambda 1 equal to 8 and lambda 2 equal to your 2, which is nothing but the eigenvalues. Ensure that you consider the highest value to be lambda 1 and the lowest value to be lambda 2. So eigenvalues have been obtained. Now from the eigenvalues we can calculate the singular values. So how singular values are calculated? Singular value 1 is nothing but square root of lambda 1, so it is square root of 8. Singular value 2 is nothing but square root of lambda 2, which is nothing but square root of 2. Now once we have obtained the eigenvalues and singular values, we can easily find out the eigenvectors. So for lambda 1 equal to 8, I will be substituting over here instead of lambda the value 8. This is the matrix. So on doing that, what are we getting? We are getting minus 3, 3, 3 and minus 3. Now to calculate eigenvectors, we consider A11, A12 and we equate it to 0. So we get two equations, minus 3A11 plus 3A12, 3A11 minus 3A12 equal to 0. Now these two equations, they can be solved simultaneously, but as we have seen in principal component analysis, by orthogonal transformation, A11 square plus A12 square is equal to your 1. So what are we doing in this case is, I am taking first equation and I am taking 3A12 to the other side, so it becomes minus 3A12 and I am cancelling the minus sign and the 3. So finally I get A11 is equal to A12. I am substituting this particular value in equation number 3. So A11 will now become A12 square plus A12 square is equal to your 1, which is nothing but 2A12 square, which is equal to your 1. Therefore your A12 square is nothing but 1 upon 2 and A12 is square root of 1 by 2. So when I am substituting A12's value in any of these equations, that is first, second or third, I will be getting A11 value to be square root of 1 by 2. So this is how we have calculated A11 and A12 when lambda 1 is equal to 8. In a similar manner, you have to do it when lambda 2 is equal to your 2. So when I am performing the same operation over here, instead of 8, I have taken here 2. I am getting two equations, applying orthogonal transformation and substituting the values, and therefore I get A11 to be minus root of 1 by 2 and A12 to be your 1 by 2, square root of 1 by 2. So when lambda 1 is equal to 8, my eigenvectors are square root of 1 by 2, square root of 1 by 2. When lambda 2 is equal to your 2, my V2 is minus square root of 1 by 2, square root of 1 by 2. Now if you remember, I told you our matrix can be divided into three elements: U, sigma and V. So now U is what? It is nothing but U1 comma U2 because it is a 2 cross 2 matrix. So U1 is 1 upon singular value 1 into A into your V1. So singular value 1 is nothing but square root of your lambda 1. So 1 upon square root of your 8. A is the matrix that is given to us in the question, and V1 we just now calculated, which is nothing but the eigenvector. So on performing the matrix multiplication, we get U1 value as 1, 0. In a similar manner, we will be doing it for U2. 1 upon singular value 2 into A into V2. Singular value 2 is nothing but square root of lambda 2. So 1 upon square root of 2. Matrix A remains the same. V2 is nothing but minus 1 square root 2 and square root of 1 by 2. So on performing the matrix multiplication, we get 0, 1. So what happens in this case? Your U is 1, 0, 0, 1. Now sigma is nothing but singular value 1 comma singular value 2 into I, and I is a 2 cross 2 matrix. So what we are doing in this case is we are going to consider sigma 1, sigma 2 and multiply with your I. And what happens in that case? This is your identity matrix. Sigma 1 and sigma 2 are nothing but the values, singular values that were obtained from the eigenvalues. Square root of 8 and square root of 2. Performing matrix multiplication gives us the value of summation. And now V1 is nothing but your V is nothing but eigenvector V1, eigenvector V2. But we need to find out the transpose. So we perform matrix transpose. So A is U summation V transpose. We have obtained all these three components or elements. So on performing matrix multiplication, you get this particular answer. And if you check, the value that you have obtained is the same. 2, 2, minus 1 and 1. It is the same as it was given in the question. 2, 2, minus 1 and 1. So this is how we can perform singular value decomposition for a 2 cross 2 matrix, which is one of the dimensionality reduction techniques. Thank you.